The Blackburn Botha entered Royal Air Force service in December 1939 as a general reconnaissance and torpedo bomber, designed to operate from coastal command stations around Britain. It had passed Air Ministry acceptance trials. It had completed structural testing, engine runs, and handling evaluations. The manufacturer had delivered an aircraft that met the written specifications in the contract. Within 6 months, squadrons were refusing to fly it on operational sorties. Pilots reported control failures, structural weakness, and engine performance so inadequate that fully loaded aircraft could barely maintain altitude on one engine. The Botha had not failed a single formal test. It had simply been tested against requirements that bore no relation to the missions it would be expected to perform, and the difference between what the tests measured and what combat demanded would kill crews before the Air Ministry formally acknowledged the problem. The Air Ministry issued Specification M.35 in 1935, calling for a 3-seat reconnaissance bomber capable of carrying a torpedo or bombs, with endurance sufficient for maritime patrol and speed adequate to evade interception. Blackburn aircraft's design used 2 Bristol Perseus radial engines, each producing 930 horsepower, mounted on a mid-wing monoplane airframe. The crew compartment accommodated a pilot, navigator, and gunner. Internal bomb bay could carry a single 18-inch torpedo or 2,000 pounds of bombs. Defensive armament consisted of a single 303 Vickers gun in a manually operated dorsal turret. The design emphasized range and payload over speed or maneuverability, consistent with the doctrine that reconnaissance aircraft would avoid combat rather than engage. Prototype testing at Bruff Aerodrome demonstrated adequate takeoff performance, stable cruise flight, and acceptable landing characteristics. The aircraft met the minimum speed requirement of 240 miles per hour. It could maintain altitude on a single engine under test conditions with reduced fuel and no military load. Structural tests confirmed the airframe could withstand the stresses of catapult launch from seaplane tenders, though this capability was never operationally required. The Air Ministry accepted the design and ordered production in 1938. Decision: makers believed they had procured a versatile platform suitable for the broad range of coastal patrolled duties anticipated in a European conflict. The specifications had been met. The tests had been passed. The aircraft was cleared for squadron service. By May, Coastal Command's operational requirements had clarified into missions the Botha was structurally and aerodynamically incapable of performing. Patrols extended over the North Sea in conditions that included icing, turbulence, and visibility near zero. Crews were expected to search for surfaced U-boats, identify and shadow enemy shipping, and deliver torpedo attacks against defended targets. These missions required aircraft to operate at low altitude for extended periods, often at full throttle, with full fuel and ordnance loads. Maintenance had to be completed by ground crews working outdoors in cold, wet conditions with limited access to replacement parts. Sorties launched on short notice, sometimes within minutes of reconnaissance reports. Aircraft that could not sustain cruise speed with a combat load, or that required excessive time to reach operational altitude, could not fulfill the mission. The Botha's test flights had been conducted with partial fuel, no ordnance, and in fair weather over land. Single Engine performance had been evaluated at light weight, not at maximum takeoff weight. The specifications had not required testing under full combat load in adverse weather. Those conditions were considered operational variables, not design parameters. That decision would prove fatal. The first operational sorties from RAF Thorney Island in early 1940 revealed problems that formal testing had not detected. Pilots reported that fully loaded aircraft required nearly the entire runway length to achieve takeoff speed, with minimal margin for error. Once airborne, rate of climb was insufficient to reach safe altitude before crossing the coastline. Several crews aborted missions because they could not climb above cloud layers that extended to 8,000 feet, leaving them unable to navigate or observe. On missions that preceded, pilots found the aircraft difficult to control in turbulence. The control surfaces, particularly the elevators, required constant correction to maintain level flight. Crews described the sensation as flying an aircraft that was aerodynamically unbalanced, requiring continuous physical effort to keep it stable. The dorsal turret, when rotated aft, disrupted airflow over the tail surfaces, inducing a pitching moment that had to be countered with trim adjustments. This had not been evaluated during testing, because gunnery trials were conducted separately from flight testing and never simultaneously under full load. The most critical failure appeared during single-engine operation. When one engine failed or was throttled back, the aircraft could not maintain altitude at combat weight. It descended regardless of pilot input. This was not a gradual loss of altitude that could be managed. It was a steady, unrecoverable sink rate that would terminate in controlled flight into the sea if land were not immediately accessible. The single-engine failure mode stemmed from a fundamental miscalculation in the design's power-to-weight ratio and the test regime's failure to validate performance under realistic conditions. The Perseus engines produced adequate power at sea level under optimal conditions, but their output decreased with altitude and in cold, dense air. At maximum takeoff weight, 11,000 pounds with full fuel and a torpedo, the aircraft's thrust-to-weight ratio left no margin. Loss of one engine reduced available thrust by 50%, but drag did not reduce proportionally. The windmilling propeller on the dead engine created substantial drag. The asymmetric thrust required constant rudder input, which induced further drag. The combination meant the aircraft could not maintain altitude above approximately 2,000 feet on one engine at combat weight. Testing had verified single-engine performance at 8,000 pounds, a weight the aircraft would never operationally fly at once it departed for a mission. The test had been passed, but the test had not measured survivability. The second failure was structural, though it manifested as aerodynamic instability. The Botha's tail structure was lightly built to save weight. Under turbulence or during sudden control inputs, the tail flexed measurably. This flex altered the aerodynamic forces on the control surfaces, creating a lag between pilot input and aircraft response. In smooth air, this was barely noticeable. In the turbulent conditions typical of North Sea weather, it made precise control impossible. Pilots could not accurately judge how much control input was required because the aircraft's response varied depending on how much the tail was flexing at that moment. Several incidents involved aircraft porpoising uncontrollably during final approach, a direct result of the flexible tail's interaction with control inputs during configuration changes. One aircraft broke up in flight when the tail structure failed during a recovery from turbulence. Induced dive. Investigation revealed fatigue cracks in the tail spar, indicating the structure was being overstressed during normal operations. The third issue was engine cooling. The Perseus engines were equipped with evaporative cooling systems that were lighter and more compact than traditional radiators. In temperate test conditions, the system functioned adequately. In prolonged high-power operation during climbs or at low altitude, the coolant boiled off faster than the system could condense and recirculate it. Pilots were forced to reduce power to prevent engine damage, which negated any performance advantage the engines theoretically provided. Ground crews had to refill coolant after nearly every sortie, a maintenance burden that increased turnaround time and reduced sortie availability. The cooling system had been tested on static stands and during brief flight tests, but never during sustained operations representative of actual missions. The fourth failure involved the bomb bay and torpedo release mechanism. The internal bay was not pressurized or heated. At altitude, moisture from the aircraft's interior condensed and froze on the release mechanisms. Several crews reported being unable to release ordnance because the mechanical linkages had frozen. Emergency manual release procedures required the navigator to access the bomb bay in flight, open a panel, and physically manipulate the release with a tool. This was difficult in turbulence and impossible if the aircraft was under attack. Missions were aborted because ordnance could not be delivered. The mechanism had been tested on the ground in controlled temperature conditions, but never in flight at altitude in winter. Squadron commanders began filing reports within 3 months of operational deployment. The tone was measured but unambiguous. 608 Squadron at Thornaby reported the aircraft unsuitable for operational use in May 1940. Pilots described scenarios where engine failure on takeoff would result in an unavoidable crash because the aircraft could not climb or maneuver on one engine at that weight. Several crews refused to fly torpedo missions, stating the aircraft could not reach attack speed or maneuver effectively after release. This was not insubordination. It was professional judgment based on observed performance. Ground crew reports noted structural issues including cracked spars, failed control cable fittings, and persistent engine overheating that maintenance procedures could not resolve. By June 1940, operational sortie rates in Botha equipped squadrons had declined to less than 30% of authorized levels. Aircraft were grounded awaiting parts, repairs, or because crews assessed them as unsafe. Morale deteriorated. Replacement crews arrived, were briefed on the aircraft's limitations, and requested transfer. Wing commanders escalated the reports to Coastal Command headquarters. The responses were bureaucratic. Modifications were proposed. Additional testing was authorized. Operational use continued. Coastal Command quietly withdrew the Botha from frontline reconnaissance duties in late 1940. It was not formally declared obsolete. Instead, it was reassigned to training units where it would operate at reduced weights, in controlled conditions, without the requirement to perform missions its design could not support. Even in training, accident rates were elevated. Several aircraft were lost to structural failure or control problems during routine flights. By 1941, the type was being phased out of training as well, replaced by other designs that, while not ideal, were at least predictable. Blackburn aircraft received no further production contracts for the Botha. Approximately 580 had been built. Most were scrapped by 1943. Official records listed the type as retired from service, without detailing why. Internal Air Ministry correspondence, later declassified, revealed that senior officers had been aware of the deficiencies as early as mid-1940, but had allowed operations to continue because replacement aircraft were not yet available in sufficient numbers. The decision was operational necessity, not confidence in the design. The Botha had passed every test the Air Ministry required. Those tests had measured the wrong things. They had verified that the aircraft could fly, but not that it could complete the missions it would be assigned. They had confirmed structural integrity under load cases that did not represent combat operations. They had validated single-engine performance under conditions the aircraft would never actually experience. The specifications had been written without full understanding of what maritime reconnaissance in wartime would demand, and the testing had enforced those specifications without questioning whether they were sufficient. The aircraft had been accepted because it met the contract requirements. The contract requirements had been inadequate. By the time operational data made this clear, hundreds of aircraft had been built and crews were flying them. The institutional response was slow, bureaucratic, and constrained by production realities. The Botha disappeared from service, not because it was formally rejected, but because squadrons stopped using it and command stopped arguing. It existed afterward primarily as a notation in loss records and maintenance logs, an aircraft that had satisfied every formal requirement and failed every test that involved actually fighting a war.